Hello everyone, this is Dr. Jacob from Jacob's Lab. I'm here to give a synthetic proposal for the synthesis of lysergic acid esters. It's based on a double manic reaction to generate the key ring of LSD. Basically, the synthesis of LSD has spanned many decades, starting from Nobel laureate Robert Woodward's first synthesis in 9 steps. One of the steps towards the end, introducing the cyano group, uses hydrogen cyanide in acetic acid, hydrogen cyanide gas dissolved in acetic acid. This is a very dangerous chemical which is hard to do in normal labs. You have to have extraordinary precautions to use hydrogen cyanide. There are other syntheses, anywhere from 7 to 10 steps in recent years. Now, they are all based on retrosynthetic analysis. Now, the idea for synthesizing the lysergic acid rings came from my studies on creating 4-piperidone ring by a double manic reaction using aldehydes and amine, in this case ammonium acetate, and ketones. So when I look at the structure of LSD, this 4-piperidone ring can indeed be generated from indoles using 2 approaches, and I will outline that. In the first approach, it's a 6-step synthesis. I am proposing a 6-step synthesis of lysergic acid ethyl ester, starting from bromo-indole. It's well known that bromo-indoles and any indole can do alkylation at the 3 position using sodium hydride and THF or alkylating agent, any alkylating agent. So in this case, I use sodium hydride and THF at room temperature with bromide of propinaldehyde. So it's a protected propinaldehyde as a diethyl acetal. Alkylation does go very well in 85% to 90% yield. And in the next key step, which introduces the required entities for construction of the CD ring of the LSD molecule. This is a Buchwald-Hartwig reaction using palladium chemistry, and in this case I use the simple readily available cheap ethyl acetoacetate, and the terminal methyl group reacts with the bromo-indole to give the product, alkylation product. In other words, the palladium 0 and the reagent helps in the alkylation of the benzene ring, displacing bromine. And there you have on the far right top, you see the resulting ketoester. Now, the next step, simply deacetylize with dilute HCl in water, you get the free aldehyde. As you can see, the middle right side, you see the aldehyde, the ketoester aldehyde. Now, here is the key step. This is called manic reaction proceeding through an aldol. Now, many people have called this reaction going through an intermediate generated by the famous Novel-Angel reaction. The Novel-Angel reaction is reaction between ketones and formaldehyde or aldehydes in ethanol with acetic acid. Remember, there is no base here. It's a very simple reaction. So in the first step, it is postulated that the Novel-Angel reaction results in the aldol product on both. In other words, if you use formaldehyde and then there is a built-in aldehyde already, as you can see. So the formaldehyde on one side of the ketone, on the middle side, in other words, the ketoester, middle of the ketoester, alpha keto next to the ester, that is attacked by formaldehyde to give the aldol, and on the other free aldehyde is attacked by the terminal of the ethyl acetoacetate product to give a double aldol. And you see at this point, this reaction in situ dehydrates and the ammonium acetate is added at this point. And in acetic acid, the ammonium acetate, after dehydration, it adds a double Michael addition. In other words, the ammonia adds to the unsaturated enone at both ends. And you see this is a double Michael reaction. Ammonia reacts with both enones to give the 4-ketone moiety. So that is the beauty of this reaction, is that a reaction is really a manic reaction to start with, but at the end you can say, oh well, this is a Michael addition to generate the final 4-peptidone ring. So it's a combination of Michael and manic reaction all in one step with no base but in ethanol and acetic acid. Now having made now we have the ring system of LSD in 5 steps. Remember, it's actually 4 steps. Now the only thing we require is this ketoester. The ketone has to be reduced with the alcohol with sodium borohydride in THF. That goes in extremely high yield at room temperature. And then all we had left to do is dehydrate using trifluoroacetic acid at room temperature in dichloromethane. There you have the lysergic acid ethyl ester. Now, the other pathway is using a more complicated, little bit more complicated reaction, dianion aldol followed by Michael reaction. In this case, it proceeds in 8 steps, so it is longer than the previous 6 steps. Now, here, basically you start with the same bromo indole and you alkylate the same way at the 3 position with the bromopropinaldehyde acetal. And there you introduce our Buchwald reaction chemistry with introducing the ethyl acetoacetate moiety on the aromatic ring. Now, the next step is protecting. In this case, one has to protect the nitrogen of the indole with benzyl oxychloroformate. And then you have to hydrolyze. After the N is protected, indole is protected, you have to hydrolyze the aldehyde, the acetal to the aldehyde. Now, having got that, one makes the dianion of the ketoester. So you get the, so in other words, the dianion is generated as shown, and if you react it with formaldehyde, you get a double attack of the formaldehyde on both the terminal and the middle carbons of the ester unit. So now you have, on protonation with HCl, you have the aldol product, double aldol product. Now, if you simply dehydrate with any acid, mild, TFA or milder, you will get the enone system required for the next step. So one can use methylamine, in which case you get the methyl ester of lysergic acid, or you can use ammonia gas. Ammonia gas will also add Michael. So, and then you get to generate the ring system, LSD. You already have everything. You just have to reduce the ketone as in the previous word. With sodium borohydride, you get very good yield, 90% yield of the alcohol. And then you dehydrate, just like before, with TFA in methylene chloride at room temperature. There you have lysergic acid, ethyl ester in 1, 2, 3, 4, 5, 6, 7, 8, 9 steps, whereas the previous synthesis was 6 steps. So hopefully this is also a practical way to make lysergic acid. Now, cost analysis shows that even if the process can chemist in 15% overall yield, the commercial application of this new chemical synthesis is practical, especially the first reaction steps, the 6-step sequence. Comparing quality and price of the finished product is expected to be within reason, as the number of linear chemical steps starting from the key indole intermediate of this process will result in the shortest synthesis of lysergic acid ever attempted. Finally, once the process chemistry is completed, right now we have only the scouting run to make the intermediates and product. Now we have to develop a process chemistry. So the future study will be to develop the process chemistry, and once it is completed, one can synthesize not only LSD ethyl ester, but many analogues of LSD with no psychedelic side effects, but with desired medicinal property for the treatment of metabolic diseases as well as neurological disorders such as Parkinson and Alzheimer's disease. Attaching other nitrogen-containing complex ring structures to the acid functionality of lysergic acid will be a simple chemical transformation of an acid to amide. So this also is a promising approach to lysergic acid analogues with no psychedelic effect. Funding for this future study is welcome, and I look forward to your responses.